Yes, yes, it is. So, I, Professor Baladath, welcomes you on behalf of Mechanical Engineering Department, A.D. Patel Institute of Technology.
Just give me a minute. Just to check something. Yes. So I will switch off the video. Is it okay?
Okay.
It's okay. Fine.
So, you can check your presentation.
Oh, that's what I'm doing. Right. Visible?
Yes, yes, it is visible, sir. Yes, yes, it is working. So it's changed. So we'll start in 5 to 10 minutes as the time is 11:45. Okay, sir.
That's okay. No problem.
Yes, good morning, Dr. Ratna, sir.
Yes. So,
Yes, sir.
am I audible?
Very fine.
Oh, let me hear that.
Okay.
How's the workshop going?
Yeah, absolutely fine, sir. We will start within 2-3 minutes. Sir.
5 minutes, sir. Okay. Fine.
5 minutes. So once again, very good morning to all. And I would like to welcome Professor Ratan Kishore Velamati, today's speaker on 4th day second sessions of the AICT AQIS sponsored Faculty Development Computational Fluid Dynamics for Role of Engineers. Before we start the sessions, I would like to introduce today's speaker, Dr. Ratan Kishore Velamati. Dr. Ratan Kishore Velamati is currently working as an assistant professor in department. That's a School of Engineering, Amrita Vishwavidyapeetham, Coimbatore. Dr. Ratna did his BTech in Mechanical Engineering from NIT Surathkal in 2002. Then after he did his MTech in Thermal Engineering from IIT Delhi in 2004. Dr. Ratan Kishore Velamati received his PhD in Mechanical Engineering from IIT Delhi in 2010. He currently works in the research area of Dr. Ratan Kishore Velamati's premixed combustion for multi-component mixture, specifically propane plus hydrogen gases, high temperature natural convection flows, and a flow through industrial valves. He is a reviewer in 7 different journals as well as conferences. He has taught various courses in UG as well as the PG level. He was involved in 3 funded research projects, out of which 2 are already completed and 1 is ongoing, with a total worth of rupees 62 lakhs almost. He has a total of 46 publications in various journals and conference proceedings. So it's really a matter of pleasure for us. I knew him very well. He's a very good in computational fluid dynamics. And I am very much thankful to Dr. Ratan Kishore for giving us time for 1.5 hours. Sir, I would request to start your presentations.
Okay, thank you very much. Now, am I audible? I just want to confirm that's all. Hello?
Yes, sir. Yes, you are audible.
That's okay. Thank you. So, today I'm going to speak mostly about, since it's the course about applied CFD, I'm focusing on one area which I work for the last 6-7 years. It is on CFD for moving objects. Okay, so CFD for rotating or flapping machinery. Okay. My name is Ratan Kishore. I'm actually working as associate professor in Department of Mechanical Engineering, Amrita Vishwavidyapeetham. So we'll get into this outline of the presentation. I will start with rotating machinery, typically their examples, and modeling approaches, introduction, and then go into some theory related to reference frames, moving reference frames primarily, and then sliding mesh model. Then we look at dynamic mesh model. The first 5 parts is more or less to tell you the theory behind how we solve for a rotating machinery. And then the case studies are some of the work which I have done. Mostly I have not done. My students have done, whom I have guided, and some of them are published, some of them are yet to publish. So, find this. So most of the engineering, a lot of engineering problems have flows through domains where they're either having a rotating or translating components. Okay. Some of the examples that you can see are translation motion is that if you have a car moving in a tunnel or a train moving in a tunnel, then one of the standard examples that we have for translation motion is there. Piston motion in IC engines or in compressors, wherever you have a piston cylinder arrangement. Then you have oscillating aerofoils, which are used for propulsion. Examples for rotating motion is very, very standard. Propellers, turbine blades, pump radial propellers, impellers, which are found. Then you have wind turbines. Wind turbines are, you have horizontal axis wind turbine and vertical axis wind turbine. We'll go into that later. Then you have combined translating and rotating motion. Okay. One of the most studied example for this is flapping wings. So people would like to know how the birds or flies would flap their wings so that you can make a small scale bio-inspired objects. Okay. Then the other naturally occurring phenomena is vertex induced vibration. So it can be both rotational and translation. Depends on how you put the constraints. So these are the examples that we see day-to-day life, where you have components which would either rotate or translate, or combination of both rotation and translation. So we generally in CFD we solve for flow over a surface, okay, or around a surface. Okay. And to resolve the phenomena, we divide the computational domain into small regions called grid. Okay. Now, how to solve for a case where grid has to move? There is a question. Okay. So let us. How to solve there? If you have a domain, your computational domain or grid is moving. Okay. There are two ways. Okay. This more or less common sense is that if I'm trying to solve something that is moving, I have two ways to solve. One, you solve it in a stationary reference frame. That means, like you have a train moving, and you're standing beside the train, and you see that the train is moving, so I can see the motion of the train. The other way is that you sit on the train, and wind will come towards you. Okay, these are two different reference frames. One is a moving reference frame, other is the stationary reference frame. Okay, so now if I solve in moving reference frame, then the equations, the Navier-Stokes equations itself would change. Okay, and generally when you solve for moving reference frame, you solve for steady state flow. Okay, solutions become steady state. Actually, when I have a motion of my object, the flow is supposed to be unsteady because my surface is moving, like a fan or a propeller or a impeller, whichever it is. Okay. Second approach is your domain's shape is changing or deforming. Okay. So that is called dynamic mesh approach, where the grid would deform or move, okay, with respect to time. Inherently, dynamic mesh approach is usually unsteady. Okay. So let us look at an example. If you have an impeller like this, okay, if it is rotating, and I'm trying to solve for the flow around this impeller, then I can always solve as if I'm sitting on the impeller, then the fluid is rotating around it. Because I'm sitting on the impeller, I'm stationary, the fluid is rotating. Okay, that is what is called moving reference frame. Yeah. Then you have dynamic mesh, where because I have a piston motion, I cannot solve it in the moving reference frame here. Okay. The only option is that I have to modify the mesh. with respect to time because the shape of the domain is changing. Okay. So these are two different approaches for solving a moving domain problems. Okay. So overall view, I usually use Fluent, but whatever I'm teaching is more generic, which is available in all the general CFD solvers. Okay. So there are primarily two approaches for reference frame. One is called single reference frame, other is a multiple reference frame. We'll get into details, each of them. And the third approach is called sliding mesh, and fourth one is dynamic mesh. The first three are included into a reference frame model. And the last one is the where you have to have a solver for meshing itself. Okay. We'll get into details of each of these, okay, individually. Let us start with single reference frame. Okay. The whole concept of single reference frame is that you have only one fluid domain which rotates with a constant RPM, either rotation or translation, whichever it is, okay, with respect to an axis. So what is the use of this? Okay, why do you want to solve a reference frame? Okay. Inherently, if I have an impeller or any object that is moving, my problem is unsteady. Okay. But if I'm not interested in what is happening behind my impeller or behind my turbine, if that is not my interest. My interest is only to know what is the forces that occur on the impeller. Okay, I'm more interested in what is happening to the impeller. Okay, some force calculation or the speed calculation or the way the shear forces are, how the mixing is occurring around the impeller. If these are my interest, then I rather not to have a completely unsteady flow problem because it is a very, very computationally expensive. Then simpler work is that I solve around the impeller. Instead of solving the stationary approach, I solve moving reference approach. So the unsteady problem becomes steady state in a reference frame. Advantages, obviously, less computational cost, easy to analyze. But there are restrictions. Obviously, when I make an assumption, I would have restriction. What is the restriction? One, when I have, wherever I put a boundary for my domain, it should be surface of revolution. Okay. Let us give an example. Okay. You have a rotor like this. If this is my stationary wall and if this is the axis, the stationary wall should be surface of revolution. That means it should be symmetric with respect to the axis. Okay. Whereas if I have baffles like this, that is not valid. You cannot solve it in a single reference. Okay. Then you will have unsteadiness because there will be vertex structures here which will not be valid. Okay. Which will not be solved and whole solution will be wrong. Okay. So, what exactly we are doing when you solve for rotating reference frames? All we're trying to do is that if I have a stationary reference, that is, you take coordinate system. Okay, this is a coordinate system for a stationary frame. Then I take a coordinate system for rotating frame, where rotation, with respect to rotation, I would write my Navier-Stokes equation. Okay, so this is a bigger picture of the reference frame direction. So R0 is the location where I made the computational domain. And instead of solving the problem in stationary frame, I would solve it in rotation frame with respect to the axis of rotation. Okay. So what would happen? This is a standard velocity triangle that we see in most of our turbo machinery course. Okay. You have your absolute velocity is a vectorial addition of your relative velocity plus rotational velocity. Okay. So of course this triangle will change the way your rotation direction would be. Okay. So rotational velocity is nothing but omega into r, where omega is your RPM or radians per second, whichever way you write, and r is your radius of rotation. So now, if I write my relative velocity formulation for X momentum equation, this is how it looks like. You will have same. You have an unsteady term, you have an advection term, you have a pressure gradient, and a shear stress term, which is your viscosity term. And all these will have a velocity, which is a relative velocity. That is this W. Okay. So everything will W. Plus there will be two acceleration terms. Okay. Because I'm solving in a relative velocity frame or rotational velocity frame, you will have two acceleration terms that will get added up. One, you have Coriolis component. Other is a centripetal component. These two components should be added to your equation. Okay. So normally in any solver, any CFD solver, usually the source terms are added into the solver itself automatically. We don't write it as a separate set of UDFs, or we are not writing it separately. It will be included into it. Then, if I solve an absolute difference frame, then you will have additional terms, but they will be together. Okay. But these terms, whatever centrifugal and Coriolis component acceleration that will come, this has to be done by the motion of the grid. Okay. This would come because of the motion of the grid. Coriolis and centripetal force would come because of the motion of the grid. Okay. Here it will come because I'm using a reference frame for the relative velocity. One second. So now it's always not necessary that I have only one entire domain is rotating. Okay. You can always have a region where certain part of the domain is rotating and certain part of the domain is stationary. Okay. For example, if you want to solve how the flow field will look like in a room. Okay. Now I have chairs, I have fans, the fan is rotating. I cannot solve entire room to be a rotating domain. That is not correct. Okay. Region around the fan is rotating and remaining part is stationary. Okay. So that means I have to have two zones, fluid zones. One is rotating, other is stationary. Okay. That is where you use something called multiple reference frame. Okay. Again, multiple reference frame has the only beneficial of multiple reference frame that a part of the domain, fluid domain, can be stationary. Remaining part is rotating. Okay. Now, still the solution will be steady state. You will not have transient solution. Okay. So let us look at what does it mean. Okay. I have, this is a conceptual image. You have a rotating zone, you have a stationary zone. In the rotating zone, you solve for the rotating Navier-Stokes, and in the stationary zone, you solve for absolute velocity, which is normal Navier-Stokes equation. Okay. Between these two zones, you will have an interface. Okay. At the interface, the solution is matched. Okay. That means the relative velocity would be matched with the absolute velocity by conversion. Okay. So you have, this is the difference between the single and multiple reference frame modeling. You will have an idea. If I have an impeller, which is for a pump, okay, I have a flow coming in like this. It will go through the impeller and it will go out. Okay, so this impeller is rotating. If I am solving for one of the passages of the impeller, like this, okay, or a blower, then I'm only solving for this region. Okay. Then in that case, you can solve it as single reference. Whereas if you're solving for the entire impeller, okay, and you want to see how the flow field will look like, then in that case, you have to solve for a part of the domain to be rotating, remaining part to be stationary. Okay. So how are you solving for that? Basically, around the impeller, you will create a concentric circle. This would be the interface, and the impeller or the blower wheel would be considered as rotating domain, and the remaining part of the casing would be considered as stationary. So obviously, when you divide the computational domain into two regions, a stationary and a rotating zone, they have to be separated. Okay, they have to be separated by an edge or a face, whichever way it comes out in 2D and 3D. So the interface is a region where I interpolate my solution. In this case, because in the rotating domain, I'm solving for relative Navier-Stokes, and in the stationary domain, I'm solving for stationary Navier-Stokes. Between them, I have to apply my velocity triangle formulation, that is a vectorial addition, to convert the relative velocity into absolute velocity. So that particular calculation and the conversion would occur on the interface. Keep in mind, multi-reference frame is still a steady state solution. Okay. What is the problem? Because the motion between the rotating zone and the stationary zone is neglected. That means whatever that happens in the rotating zone, its effect on the stationary zone would not be modeled completely. Okay. So in general, it is called a frozen rotor approach. This is a standard term that they use in the general CFD. Okay. So there are two kinds of interfaces that we can have in any CFD solution. One is called conforming interface. That means the edge that is between these two faces would be having grid will match with each other. Okay. The other is non-conforming interface. That means the grid will not match with each other. That means there should be interpolation between these two solutions. Okay. So you will have an algorithm that will make sure that the solution on one face would be interpolated to the other face, or one edge onto the other edge. Okay. So now again, you will have the same problem that we had previously, like you have your SRF, single reference frame. The wall should be surface of revolution. Same thing is here. If you have an interface, the interface shape should be surface of revolution. If you don't have surface of revolution, then it will not work. Okay, that means this interface between the rotating zone and the stationary zone should be circular or cylindrical in 3D. It cannot be elliptical shape. Elliptical shape is not a surface of revolution. Okay, that is the one of the standard thing that you need to look at. Okay. Now, surface of revolution has to be such that if I have an axis with respect to axis, if I am rotating, it should be symmetric. Okay. No. So one can ask, okay, well, what will happen if I'm solving for a large turbine? Okay, wind turbine, not wind turbine, you have your gas turbine, which is like huge number of blades. Then you can always use the solution. You can only solve for part of the compressor or a turbine stage using a periodic interface. Okay. So most of the reference formulations will allow you to solve using periodic interfaces. Periodic interfaces are where this and this side of the turbine blade would be periodic with each other. Yeah, that means you are solving for a part of my whole turbine, still getting the physics completely. Now, so one can say, okay, it's easier to solve in steady state. Why exactly we need to worry anything else? Okay. But there are concerns. There are concerns because when I'm solving for a reference frame, around this blade, which is solved as a rotating reference, and I would solve a rotating Navier-Stokes equation. Along the wherever you have stationary, you will solve a stationary Navier-Stokes equation, and you will interface the solution at the or interpolate the solution at the interface. This looks fine, but the only consideration is the solution is steady state. There are a lot of unsteady phenomena that occurs because of rotation. One such thing that will happen is vertex interactions. For example, if I have blade, there is a stator and a rotor. Okay. And the flow stator is the place where it is a nozzle shape, which will increase the velocity, which will hit the rotor, so the rotor rotates. Okay. There are potential interactions that will occur. There are either wake interactions, you have shock interactions, you have pressure waves. These are all unsteady phenomena that will occur from the stator. So if it is close to supersonic, you'll have shock waves. You have wake that will occur in most of the any flow phenomena. You'll have wake interactions. If you have to resolve these conditions, wake and shock interactions, you have to solve unsteady flow. It is not possible to solve these in a steady state flow. Generally, multi-reference frame would neglect all these unsteady interactions. They're only valid, multi-reference frame is only valid when these interactions are negligible effect on the parameter of your interest. So it depends on what we are trying to solve for. Okay, if it is having negligible effect on the parameter of your interest, then you are free to use your multi-reference frame or single reference frame, whichever way it looks like. But if the unsteady interactions are having heavy effect on your parameter of interest, then you do not have any other option but to solve for a problem where the grid is moving. Okay. One simple way of moving the grid is called sliding mesh model. It's an extremely simple geometrical way of solving things. Okay. What is the sliding mesh model? Is that you have a rotating zone and a stationary zone, like you have your moving reference frame. They are separated by a non-conforming interface. Okay. What is non-conforming interface? If you have not understood that part again, I will show you. That means the rotating and the stationary zone at the interface, the grid will not match one-to-one. Okay. That is what is called non-conforming interface. Okay. So if I have a non-conforming interface, sorry, wrong slide. If I have non-conforming interface, the rotating zone, I can rotate the grid with respect to time. Okay. So that means I have a moving mesh zone and I have a stationary zone. Moving mesh zone will move with respect to time. So I know if I have to specify what either the translating velocity or the rotating velocity with respect to time. If I mention that, then I know how this grid, okay, one grid, if you take the blue one, how much distance it will move with a given time, t plus delta t. Okay, and then I can interpolate the solution properly at the interface. So what is the difference between MRF and sliding mesh model. In MRF, wherever there is a rotating zone, you solve a rotating Navier-Stokes. Stationary zone, you solve a stationary Navier-Stokes. Here, in the sliding mesh model, you solve the complete domain using stationary reference frame equation. Stationary Navier-Stokes, which is a normal Navier-Stokes that we use. Okay. Now, how would you get your centrifugal force and centripetal acceleration? Okay. These two are inherently part of the solution because my mesh is moving. Coriolis centripetal acceleration both would come because my mesh is moving. Either it is rotating or translating, a combination of these two. Okay. So obviously the acceleration term will be there because of the motion of the solid itself. Okay. So acceleration is included. You don't have to solve it separately or put it into the down equations. Okay. So this is the illustration graphically. Like you have only one stationary reference and my domain is moving with respect to time. Physically, my computational domain is moving with respect to my axis of rotation. Okay. So again, the restriction still exists that my sliding interface for the sliding mesh motion should be surface of rotation. It must be surface of rotation. If it is not, again, sliding mesh motion will not work. Okay. Your solution will not work at all. Okay. So then last one is, which is normally available in most of the works which I have taken from Fluent, is dynamic mesh model. People use different names. Primarily what dynamic mesh model is that you have one of the boundary moving, like your piston cylinder arrangement. Examples that I've listed here. You have automotive piston moving inside a cylinder, flapping motion, okay, valve opening and closing, or any object or any pipe or flexible surface which is moving, contracting and expanding. Any boundary that is moving or object that is moving. So you are inherently, if it is a rotating kind of surface, yes, I can use sliding mesh motion. But sometimes it's not possible. It's not possible to have surfaces which are having interfaces with surface of rotation. Okay, so surface of revolution. The only option that you have there, that the mesh should move. So when mesh is moving, obviously you will have a complete set of one set of equation to calculate the mesh motion. To calculate the mesh motion. Okay. So dynamic mesh motion, okay, model, you have several algorithms to make the mesh motion to move or mesh to move. One is a standard, these are three standard approaches that are available. Spring analogy, local remeshing, and layering. Okay. Spring analogy is very easy to understand. If I compress, spring will get compressed. Similarly, if I have piston alignment, if I compress if I move up, the volume of my fluid motion inside the cylinder would reduce. So the mesh also will get compressed like a spring. Similarly, you have a local remeshing where around the surface where it's modifying a lot, you remesh it. And you have layering where you remove certain layers as the mesh is getting compressed. Of course, I will not get into more details of this. The last one, which is very, very important for most of the practical applications, is called 6 degrees of freedom. Okay. So you have problems like where because of the aerodynamic forces that you calculate or the moments that you calculate, the object should move. Okay. That is where you use vertex induced vibration, or if I have a turbine, and then because if I just give you the flow, the turbine should start moving. Okay, the starting part of the turbine motion, or if you have a strong wind, you naturally see that most of the trees would bend, or you have any structure that is flexible would bend. Okay, so generally 6 degrees of freedom is used for rigid body motion. Okay, of course you have if a structure is bending on its own, then it is not exactly 6 degrees of freedom motion. You have to use what is called fluid structure interaction. Again, that is also a dynamic mesh motion problem, but the structure has to be solved along with the fluid flow. Okay, that is a quite complex problem. We'll look at that some other time. These are some of the publications which I made. I have been working on wind turbines. I don't work on. There are two classifications of wind turbines. One is vertical axis wind turbine, other is the horizontal axis wind turbine. I just want to check again. Is my presentation going well? You're able to hear?
Yes, sir, it is going well.
Okay, thank you. So now I would show you some of the results which I have made publications of. So one part is I have been working on wind turbines, which is vertical axis wind turbine. Vertical axis wind turbine has certain advantages, which I would illustrate now and show you some of the results which I have got. Then the other part of the work which I have been working is on aerodynamics on oscillating, rotating airfoils, and try to study what would happen if I change the motion of these aerofoils, how would it affect the flow field, how would it affect the parameters which I am interested in. And I have added one more case study. I'll see if time permits. Okay. So let us start with vertical axis wind turbine. This is actually work done by one of my PhD students. So most commonly seen wind turbines are whatever you see here is called horizontal axis wind turbine. They are quite big. The largest one that is currently existing is close to 15 megawatt. The radius of the turbine is close to 300 meters. They are mostly offshore. Okay. The other classification of wind turbine, this is axis is horizontal. Then you have another classification is axis is vertical. Okay. What you see in this GIF that is there here. Okay. What is the advantage of vertical axis wind turbine? One of the major advantage is that you can place the generator on the ground. Okay, because here generator is kept in a nacelle, which has to be lifted all the way until wherever the turbine is located. Okay, sometimes it is very close to, if I have turbine with radius 300 meters, obviously I would have my structure which is as high as 500 meters. Okay, so I have to raise the whole generator onto the top of very close to the turbine. Whereas for vertical axis, I can place the turbine at the ground or at the free sea level. But obviously, if I have, then it is very low wind speed operation. And the other main advantage is that it is very tolerant to turbulence. Okay. Obviously, because the axis rotation is omnidirectional, that means the wind can come in any direction except from that is not really valid. So obviously, if it is perpendicular to the axis, it is very good. Directionality is not a problem. Okay. Now, if you have any engineering system, if you have advantages, obviously you have disadvantages. Two major disadvantages are one starting torque. Okay. That means turbine will take time to start. Okay, it has issues with starting. Then second one is I have a shaft and this blade is coming in contact with wind for only certain amount of rotation, because of which loads on the blade would be not be uniform. So the structure will take that non-uniform loading, and because of that, your structure will undergo fatigue loading, especially the shaft and the structure below it. The chance of failure are really high. The fatigue is something that you are not very much interested to put onto any structure. So the ripple effect of on the turbine shaft would cause the failure in very long term. So there's some way that ripple effect has to be. So the way we were looking at the ripple effect to reduce is most of the standard wind turbines for vertical axis are straight blade VAWT. We have been working on to look at non-straight blade. Okay, one of them is called egg beta shape, which is now named after a person who actually invented that, Proposkin. The other one is helical turbine. So these two are difficult to fabricate, but at small scale, basically, if you look at 1 kilowatt, 2 kilowatt kind of turbines, yes, it's much easier now because of 3D printing. Okay. So let us look at what are the parameters of interest. The turbine, you're looking at aerofoils. So their geometric parameters generally denoted as solidity, pitch angle, aerofoil shape, aspect ratio. So I will explain what is solidity. Solidity is defined as number of blades into chord of the turbine divided by the diameter of the turbine. Chord of the aerofoil, sorry. Okay. This combines three features: number of blades, chord, and diameter of the turbine. Okay. Then you have pitch angle. Pitch angle is how the aerofoil is placed with respect to the surface of rotation. Okay. Then aerofoil shape. Aspect ratio is chord to height of the turbine. The geometric parameters that are of interest for any vertical axis turbine. Of course, we are not looking at these. We look at mostly operating parameters. One of the non-dimensional operating parameter is called tip speed ratio, which is the rotational velocity of the tip by free stream velocity. Okay. And the performance parameters are normally the moment coefficient, which is torque divided by the non-dimensional form of the torque, in fact. And there's a performance coefficient, CP, which is power extracted by power available. Power available or energy available in the wind in that region of the turbine where it is located. Okay. So this CP for a horizontal axis wind turbine, this has a limiting value called Betz limit. And this Betz limit is slightly different for vertical axis wind turbine, which is not exactly same as horizontal axis. So how we solve this? So obviously I have a turbine which is rotating, which I explained. Here I have aerofoil which is coming in contact with wind, which will generate lift force. So they have vertex structures that are there, so it is completely unsteady flow. So I have to solve for a stationary. There's a rotating domain, there's a stationary domain. and I have to use a sliding interface. I'm not solving using moment reference frame, primarily because there are unsteady features which I need to resolve. Okay, so this is the kind of mesh which we made for a helical grid. We made a grid which is rotating helical. That is how we made the grid. Typically, very close to the turbine blade. We made the grid very fine because that is where the shear stress and the pressure profile has to be calculated properly. And as we go away from the turbine, the grid is coarsened gradually. Okay, so typically this is the turbine which I am modeling was a real scale turbine. It's not a laboratory scale. The turbine diameter is 2.7. Height of the turbine is 3 meters. It should produce close to few kilowatts. So you can see how the grid is rotated helically. Means we rotate the grid helically so that still it becomes a structured grid. Okay, this took sufficiently long time to make this grid. Of course, there is easier way to make this grid now. Now I don't use this. I'm using the ANSYS machine, Fluent machine that comes along with Fluent, where you can make meshes for complex surfaces using polyhexacore. One second. Okay. So then I had, as I showed you, there's a second turbine which we modeled, which is a troposcape turbine. So here I can put a symmetric boundary condition. Obviously, here I don't have a mesh which can be rotated the way helical turbine is. So I made an unstructured grid. Okay. So if you look at the boundary conditions, I would have a rotating domain. I have a stationary domain. One side I have inlet flow velocity, wind velocity, and both the sides of my domain are far away from the turbine. Am I audible?
Yes, sir.
Thank you. Your sides are far away from the turbine, where I can put a zero shear. And behind the turbine, I would keep the domain really large so that the pressure effects would not come. So the outlet is kept as pressure outlet, basically where the pressure would be very close to atmospheric pressure again. Okay. So what is my interest? As I told you before, my interest is to calculate how much is the power that is generated by turbine. How are we solving here? I am rotating my turbine. That means the region around the turbine, which I have indicated as a rotating domain, with a fixed RPM. Okay, how will I calculate that RPM? Because I know my wind speed, which I am giving here as at the inlet. Okay, then based on the tip speed ratio, I'm going back just to show you the formula. I would fix what tip speed ratio I want to solve. But I know the radius of the turbine, and I know my U infinity, which is my wind velocity. Calculate omega. My rotational speed, either in radians per second or revolutions per second, whichever way it is, you have to give it to the solver, and based on that, my grid would rotate. Now, inherently, sliding mesh motion solver in any CFD solver, CFD software that we take, is unsteady. That means I need to give time step size. Okay. So since I'm rotating my turbine, usually the most standard practice is that each time step is given with respect to degrees of rotation. Okay. like I can give one time step size such that every time step it will rotate by 1 degree of rotation. Okay, here we did calculation for every 1 degree of rotation as one time step. So what we are interested, we are trying to get the torque. The non-dimensional form of the torque is called coefficient of moment. Okay. Torque is nothing but moment with respect to axis. Okay. So you can see here, I plotted the moment for all the 3 blades with respect to cycles. Okay. Cycle is 1 cycle is 360 degrees. I have done for 10 cycles. You can see, as initially there will be, because of initial condition, the solution will not be good. As you go on, you can see 8, 9, 10 cycle, they are repeated. It will become periodic. Okay. Now, obviously, if I'm using 14 million cells, so if I use a 40 core, 20 core machine, it will take 5 to 6 days to do one simulation. Okay. So pretty computational expensive because this is the unsteady solution. Unless I get this periodic solution, it's of no use. Okay. No. What is mostly interesting to us is the average CP or coefficient of performance. That should not vary with respect to cycles. So the last 2 cycles, the CP is almost same. So we take the CP value for different dispute ratios. Okay. So the first study that we published recently is effect of wind velocity on proposed skim blade vertical axis wind turbine. So why to study effect of wind velocity? Okay. Normally in straight blade, okay, we don't expect that wind velocity will affect the performance and all. It will have some effect, but you don't expect to be so much because entire blade is going through same wind velocity and the relative velocity remains same because you understand the relative velocity here. Because absolute velocity is what is coming as the part of the wind plus rotation. Okay, so it will not vary a lot. Whereas proposed skim blade, you will have that problem. Okay, I will show you proposed skim blade again. See, here the radius is changing. The radius of the blade is changing with respect to height, z direction. That means omega r is changing. So you expect that each section of the aerofoil is encountering different velocity or different Reynolds number. Okay, so we were interested to see what would happen if wind velocity is changing. Okay, so we have done the simulations for different wind velocities, 6 to 14 meters per second. And this is how the coefficient of performance would vary with respect to dispersion. So now one can ask, okay, why are you plotting things with respect to dispersion? This is the academic way of looking at it because the non-dimensional numbers are easy way to analyze results together. Okay, we don't run dimensional quantities. So you can see here, the funny thing is at low dispute ratio, the wind velocity makes a lot of difference in performance. That means the rotation speeds are low. Whereas when you go to optimal dispute ratio, the effect is very minimal. Okay. The effect is not significant as you see in low dispute ratio. Okay. So you can plot the same thing here. So for dispute ratio 2.5, the effect is very small and change is linear, more or less. At a low dispute ratio like 2, as the wind velocity changes, the CP changes significantly. Okay. So what is the best part of doing safety simulation is that you can go into flow features. So I'll skip this. Okay. You can go and see the flow features. Okay. Here we have taken the vorticity contours for two different velocities, 8 meter per second and 12 meter per second, for tip speed ratio 2. So you can see this is a zoomed version. You can see the lower half is for the tip, that is the bottommost part, and the first two rows, top two rows, are for the symmetric section and the mid section. They are in two different scales, so do not get confused. Okay. When you go very close to the tip, the shaft, which is like a stationary cylinder, which will have vertex structures, which will interact with the turbine blades. Yeah, and whereas the symmetric section and the mid section interactions are minimal, and the turbine would produce more power. Of course, you can see more complex phenomena which has to be explained further. We'll just then what we were interested to look at is what will happen if I have a blade which is helical. So one of the disadvantages that is there for vertical axis wind turbine is that ripple effect. So the blade loading is not uniform. So only way to avoid that is that you twist the blade. That means blade would come in front of the wind for a significant portion of my rotation. Okay. So we try to do three different helix angles, 60, 90, 120. Okay. 120 is a unique case because always one section of the blade is always in contact with field. Okay. So the helix angle is defined by psi, rotation angle is defined by theta. So let us look at the results. Again, we actually ensured that we ran several cycles of turbine and looked at whenever it becomes cyclic, we take the result. So here again, we did a turbine size which is more what you call commercially viable, to put it, not a laboratory scale. So the turbine diameter is 2.7, height is 3 meters. 3 meters is like 2 times the height of a person. So typical average height is 1.6. Can you imagine? So given that, we have done for 3 helix angles compared with straight blade. You can see that here. The black one is for straight blade, blue one is for 60 degree, and green one is for 90, and the red one is for 120. For this configuration, we have seen the 60 degrees performing better than straight blade, 90 degree, and 120. Okay. Of course, that is not the only consideration that we have to look at. We'll come back to it as we go on. And as the helix angle increases, the peak CP would shift towards higher respiration. Okay, that's two observations. Of course, this is again, the CP value is an average value. To understand why it is happening, this phenomena, everything you need to go and look at details. What are the details? Each of these values that you find, each point that you find is one simulation completely done for 6 to 7 days, depends on how much is prepared. Okay. So each simulation is nothing but average of CM multiplied with tip. Okay. So let us look at individual blade CP. So obviously you have 3 blades. One blade, if you take, azimuthal angle is your theta. Okay. So what I've plotted here is the CM, the non-dimensional torque with respect to rotation. Okay. So you can see as the blade helix angle increases like 60, 90, 120, the region where the power is extracted, the base of the peak that you see is increasing. You can see here, the power starts getting, the positive part of the CM curve would start close to 60 degree and it will end at close to 225. Here it starts at 45 degree and ends at 225. Here it starts at 30 degree for the curve which is in blue. Okay, and set 180. Okay, I'm sorry, close to 200. So the 120, the peak is very broad. The curve base is very broad. Why? Because turbine is interacting with wind for a longer angle of rotation, larger angle of rotation. Yeah. So if you want to compare ADIT ratio, it will be easy to understand. 2.3, 3.1, 2.9. You can very clearly see that as the side, which is your helix angle, 0 is for straight plate, 60, 90, 120. As the helix angle increases, the base would increase. Okay. So now, it will be interesting to see what is happening to this contribution. Okay, you have this curve. You have to understand what is happening to how it is getting produced. Okay, so we try to analyze in a slightly different way. We have taken the summation values, like I have a turbine, wind direction is in y direction, and you divide the whole rotation into 4 parts: upwind, leeward, downwind, and windward. Okay, these are just terms. This 190 degree upwind section is where the turbine will come in contact with wind. Downwind is the region where it will never contact with wind. Windward and leeward it will come partially in contact with wind. Okay. So if you look at the red color indicates for the straight blade, and the exactly opposite is your violet. Okay, indicates your 120 degrees helix angle. Look at it here. Normally, what will happen? The blade is straight. Then, in the upwind is the region where the blade will come in contact with wind. That is where it will produce the power, other torque. Okay. So you can see for all the different ratios, 2.3, 3.1, and 3.9. Straight blade will only produce significant portion of the torque only in upwind. Okay. Whereas as the helix angle increases, the torque production would be shifted from both upwind and windward. Why is that? Because the turbine, the reference, how do you say for helix, it is not exactly like you cannot put a statement called where the turbine blade is, because turbine blade is not planar. No. So the reference for us to say whether it is an upwind or the windward is that for us the reference is the bottom side of the turbine. Okay. That is how we kept the notation. So for helical turbine, the production would become more uniform because it is generating in 2 quarters. Okay, 2 quartiles, if you want to state it. Okay. Then what we try to look at is that ripple effect. We averaged everything, took a standard deviation of CP, which will represent the ripple. So standard deviation for CP for 120 is very small. For straight blade, it is very large. Okay. So if you want to reduce the ripple effect, at the same time, you want to have 160 degrees also having a very large ripple effect. want to have a less ripple effect and have more CP, the best option is to choose 90, which is trade-off between straight and helix. Okay, sorry, trade-off between power and ripple effect. Okay, so 15 minutes more. You want to go into details in terms of understanding that because I have a blade which is sweeping in helical shape, I want to see what is happening to individual sections, how they are producing, how they're getting affected because of the wind power extraction. So we divide the blade into 3 sections, and leading edge section, which is denoted as red here, and the mid section, which is green, and the trailing section, which is blue. The rotation is in anti-clockwise direction. Okay. So we plotted see the torque production from 3 sections along with the total torque production. So the black one is for the total one. Red, green, and blue are for the leading, mid, and the trailing section. You can see very clearly the azimuthal angle is always with respect to the bottom of the blade. Okay, so you can very clearly see what is fascinating to us is that the trailing section would produce as good as the mid section. Okay, the leading section is producing less power compared to other 2 sections. But if you look at it, actually, it is, if you look at the intuition, if you have a turbine, both the leading section and the trailing section should produce similar amount of power. Okay, but that is not the case, primarily because the vortex interactions are reduced for trailing section compared to the leading section. Okay. So, and then we looked at what is happening with respect to individual contributions. Right? You can observe that. So, to understand the flow field, we have actually plotted the vortex magnitude or vorticity magnitude at different sections and try to see whether how the vortex blade interaction is occurring. Cool. These are quite complex. You can see, in general, I will make a comment. For 60-degree, the vortex interaction is less. 90, the vortex interaction is more. And 120, the vortex interaction becomes enormously high. Okay. So with this, you can understand this vortex interaction from a leading edge turbine blade would be high with the other blades. Okay. That can be seen very, very clearly. I would go back again to look at the CM curve. You can see the vortex interaction is significantly high for 120, which is in okay. What is this color? Violet. Okay. So you can see that vortex interaction for the blade is really, really high for 120. Okay. So the production in because the secondary interactions is high for 120 degrees. Okay. So those can be seen in the flow field, which is the whole advantage of solving full CFD. Okay. This is one work that we have sent for publication recently. The other part of the work which I have been doing is oscillating rotating aerofoils. We can term the same thing as pitching plunging aerofoils. So if I do a pitching plunging for an aerofoil, that is oscillating rotating aerofoil, you can either generate thrust for propulsion, which is close to your flapping wings of insects, or you can generate even power. Okay, so how do you define that? Okay. We worked on both the regimes. The work is a part of a BTech project, actually. So the whole interest of the work is to understand effect of various operating parameters on unsteady pitching heaving aerofoil. We try to study what would happen if my profile motion is sinusoidal or non-sinusoidal motion. Okay. Our interest here is lift force, lift coefficient, drag coefficient, and moment coefficient. And the parameters that could change are oscillating frequency and heaving amplitude. Okay. So we try different parameters. If it is for propulsion, my interest is to get more coefficient of drag. In effect, drag force is nothing but its opposite to thrust. Okay. If it is the power, if I want to extract power, so what is the difference? In case of propulsion, I need to give motion and the object will move. In case of power extraction, I have a flow which will cause the motion, which will give me power. Okay, so let us go back to the aerofoil. This is aerofoil terminology. I have angle of attack, which will change because of the relative velocity. I have leading and trailing edges. That is, leading edge is the edge which faces the flow, trailing edge is opposite. And then you have two surfaces, one is suction side and the pressure side. Okay. This is what is interesting phenomena, which is relatively new, is that you have a criteria called feathering criteria. So if I keep this feathering criteria, which is theta naught is the angle of the aerofoil, okay, and you have an arctan which will speak about the effective angle of attack. Okay, so if I keep the feathering criteria less than 1, that means as the aerofoil goes through a sinusoidal motion, always the angle of attack would be negative. Okay, because of which you would get thrust. If I keep a feathering criteria greater than 1, then the angle of attack will always be positive, which will generate power. Okay, so this is the general criteria. You have feathering criteria psi equal to 1, which is the limiting case. If I have psi greater than 1, you have power extraction. If psi is less than 1, you have propulsion. So oscillating rotating aerofoils can be used for propulsion or can be used for power extraction depending on which regime you fall with. That is the feathering criteria that we have. Okay, I worked on both sides. So you have two motions here for aerofoil. One is oscillation, other is rotation. The rotation, not exactly rotation, oscillating, pitching motion to be. The pitching motion is theta is sinusoidal motion, where theta naught is your maximum angle, and heaving motion or the translation motion, the amplitude is denoted as h naught, and both this oscillating and translating motion or heaving motion is offsetted by or offset angle, which is phi. Of phase difference is phi. Okay. If you don't put this phase difference, you will not get power extraction. Okay. So that you can see here, they keep a phase difference between these two motions. Okay. Feathering criteria would give you that. So objective of this work is to make sure that you study what will happen if this motion is sinusoidal and motion is trapezoidal. Okay. Now, the funny part is here I have a motion which is oscillating and rotating. Okay. So I cannot use sliding mesh motion. And last few years, Fluent has implemented, and most of the other CFD softwares implemented a meshing technology called camera mesh. Fluent uses a word called offset mesh. Actually, the term which is most of the CFD community uses a word called camera mesh. Okay. What would happen here is that in camera mesh, you can see here, I have a foreground mesh and a background mesh. Okay. So the advantage here is that the foreground mesh, I can move it whichever way I want. And the interface of these two, foreground and background mesh, will be taken care at the place wherever the mesh would move. Okay. So now, the only thing that we need to maintain is that wherever there is an overlap region for the background and the foreground mesh, the mesh size should be similar. That is the rule. Okay. If you follow that, it will absolutely work. Okay. So you can see here there are two meshes. The blue one is one domain, two domain, then the background mesh. Wherever these two would meet, okay, that place you make a boundary interface. Okay, it's a mesh interface which would change with respect to time. The only problem with this implementation currently is that it is first order in time. So the accuracy would go down. Okay. So obviously we solved for a very low Reynolds number. So solution is for simple laminar flow. Okay. We validated with experimental results that are available for a Reynolds number of 1100. Sorry, it is not good. And we checked whether our methodology is really good. We found it is operating well. So, how much time I have? I have 5 minutes, so I'll just skip it a bit. Okay. So we try to see what will happen if I have frequency of the oscillation and rotation if it increases. Obviously, if I increase the frequency, the thrust which I get will also increase. Okay, but the increase is not linear; it is non-linear. Okay, so we try to look at what is happening to the thrust. See, thrust is always in x direction forces, and it is not the lift side; it is the drag side, which is in the direction of the flow. Okay, so if I take care of all, there are two sides: the suction side and the pressure side. Thrust is primarily because of the leading edge. Primarily. And thrust is primarily because of the leading edge, and that too because of the pressure difference. Okay, so we try to analyze that you have K.5 and K1 frequency. We try to see what will be the pressure profile at different time. Okay, so 0 at the first peak, lowest point, and the middle. Okay, so that is how we plotted. We can see at the peak, you can see that there is a huge pressure difference at the leading edge, which will give you a pressure force, which causes the thrust. Okay, as the K increases, this pressure difference increases at the leading edge, and which will give you more thrust. Okay, so just to illustrate how that looks like. Sorry, there's a video that has to play. 1 second. You can see here, okay, primarily if you go see this vertex that comes here would cause all the difference. Okay, this leading edge vertex, when it happens, this leading edge vertex, this top portion, would cause the pressure difference. Okay, so when the vertex structure forms, you will have a pressure difference between the top the suction side and the pressure side, which would lead to more thrust. Okay, so we try to analyze that at the leading edge section how it is happening, and at the intermediate section how it is happening. Okay, which would give us an idea how thrust can increase if I increase the K, my frequency. Okay. So the other parameter that we looked at is what will happen if I change the heaving motion effect of H. Okay, if I increase the heaving motion amplitude, obviously my thrust will increase. Okay, so what is the effect of that with respect to pressure and analysis of that? Okay, you can watch the video. Sorry, I'm more looking fast. H1 would go, amplitude is high, so the thrust will be high. The vortex interaction that you see in the bottom and top, the magnitude of that would increase, and which would lead to more thrust. Okay. Sorry, so we are short of time. I think I've already close to 1:15. I would stop the presentation. I actually had some other slides available on oscillating rotating square. I would request people to ask me questions if you have.
So I would like to ask participants any question?
Yes.
Sir, I would like to ask one question. What is the role of turbulence in such study? How much the result will be affected?
No, see, it depends on what regime that you're solving. So wind turbines, which we solved, helical turbine, we solved turbulent flow.
Yes.
Yeah, if they're not greater than 10 raised to 4, 10 raised to close to 10 raised to 4, the regime would be neither laminar nor turbulent, especially on aerofoils. And you solve for transition regime, you have to solve for turbulent flow. Yes, turbulence would affect.
Okay.
Of course, it depends on what kind of solution that you're making.
Right.
If you're solving for acoustics, then it will be more complicated.
Okay. So,
So
sir,
most of these flows, especially when you go for a large flow rate, flow will be turbulent. So the turbulent flow would affect my solution. Numerically, what we solve is you solve for different turbulence models. The best turbulence model for URANs that is available is STTP omega.
yes. Okay, sir. So we have maintained this practice throughout this workshop that if participants wants to ask question at a later stage, so they can send their questions to me and I'll compile them and will send you to you.
That's no problem. That should not be an issue. Okay.
Yes, sir.
That's not an issue.
So with this, I would like to thank Dr. For sparing his valuable time and giving us insights about vertical axis wind turbine, particularly, as I said, because the case study he presented, and it was such a detailed study, and it is very much helpful in harnessing energy, as we are aware that if we look at our country, we are still at certain scarcity of electricity, and by using alternate energy sources, which is answer of the scarcity. So I'm sure this has been implemented at his end at Coimbatore, because the nature or the geographical coordinates may allow the same. With this, I would like to thank you, sir. Thank you so much.
Thank you very much.